Thank you all for coming today to, I believe, the last ISR Distinguished Speaker of the year. We've had some excellent talks. We're looking forward to one more. My job is simply to introduce Lionel Briand, who is coming to us from Luxembourg. He is my co-conspirator in being the ICSE 2014 program co-chair. So he's actually spent the past 2 days with us already, where we frantically have been doing things, preparing for the next ICSE. And he's actually off to the current ICSE next week, because that's all, of course, in San Francisco. Lionel, we've known each other for quite a while. He has a very distinguished career. Has been in Fraunhofer, has been in Ottawa, has been in Norway, is currently in Luxembourg, where he was recruited to set up a new center. A center that focuses on software engineering, but especially also on impact on industry and actually industry collaborations. This is something that has run through his career for a long time. And actually he's the recipient of the IEEE Harley Mills Award, which actually looks at both innovativeness of your research and the impact that it has, out there in the real world. And so without saying much further, because otherwise I'm just going to take your time, I just want to say, Lionel, thank you for being here. We look forward to your talk. Thank you.
Thank you. I would like to thank you, André, and everybody else who has been so welcoming in the past couple of days. My first time in Irvine, so I'm happy to.
It's still really quiet.
I'm still.
There we go.
My first time here, so I find that to be a very beautiful campus and a very beautiful area. So you guys are very lucky to work and live here. So first, something I should clear up. Where is Luxembourg? And, oops, it's not very clear. But anyway, it's a small country between Belgium, France, and Germany. There are actually 3 official languages in Luxembourg: French, German, and a German dialect called Luxembourgish, which is never used except in private conversations between certain people. It's a very small country, as you can tell, and it has a small population, and the vast majority of the people there are actually foreigners, not locals. So that makes it quite unique. And it's one of the wealthiest countries in the world, and at some point in time, they used to send people abroad to study, to the UK, to North America, to France. They decided that they needed a university, not for educating people, but for research and innovation, in order to diversify their industry that was too much reliant on, the financial industry.
Higher.
Okay, all right. And so they created a university, and it's very recent. The PhD program started in 2007. They created a new center that was considered a national research priority on ICT security and reliability, where I'm working. I will tell you more about that. And it's very international. There are 3 official languages: English, French, and German in the university. If you are in computer science, you work in English. But if you are in law, you work in French, because the law is written in French, etc. So it's a very interesting place.
Actually, to say challenging.
Well, And this is where I work. This is the center, Interdisciplinary Center for ICT Security, Reliability, and Trust. It was created in 2009, and we already have 180 staff members in 3 years and a half, 20 industry partners, and I am basically the scientific director of a lab of about 15 people, 20 by the end of the year, and I work with 4 partners in the financial, satellite, automotive industry, and the government as well. And the way I work is rather unusual, if I compare to the research paradigm that most of my colleagues follow. What I'm trying to do in order to increase the impact of my research is not to work on research problems that I've defined by reading other researchers' papers, but by defining problems in collaboration with industry partners and decompose and reformulate those problems so that they can be tackled in a stepwise manner and so that they are expressed in a scientifically acceptable form. But in the end, the point is not only to be innovative, it's to have impact. So basically, we share our time between research and knowledge transfer. But the knowledge transfer goes in both directions. We learn a lot from our partners as well. You know, it's not just us teaching our partners. And you end up working on problems that are very surprising when you do that. Things that are not very much addressed in the research literature. And I'll show you examples of that. And those are the objectives: to do research-informed by practice, to have well-defined problems in context, and realistic evaluations. The work I'm going to present is work that I've conducted with many postdocs and students who are listed here, and I probably have forgotten people. So, now, in the title of my talk, I have the word model-based. Why? Why do I emphasize that term? Well, one reason is because I think we are an engineering discipline, and I don't know of any engineering discipline that does not rely on models. But many people disagree with that. I mean, you know, many people think that a model-driven approach to software engineering is not practical, useful, you know, scalable. But as I hope to convince you, when you work on testing and verification, like I do, in most cases, this is the only way to effectively automate testing or verification. I mean, I'll show you a number of examples. And honestly, in most of the problems I have addressed with industry partners in the past 15 years, there has been cases where I didn't have to rely on model-driven engineering, but for most of the problems, I don't know how I could have tackled those problems other ways. But of course, models have many other purposes besides testing and verification, and such as improving communication and support requirements and design. You know. And there are many, many ways to model a system in the environment. A very large number of ways. There are standards, of course, like the UML and its extensions, such as MARTE for real-time systems, SysML for system engineering, and others. But in many other more academic methodologies. But we will talk about that. We'll talk about how to make choices about that. Basically, we see that how you model is driven in a given context by the application domain, whether there are standards that are imposed in a given domain, industrial domain, the practices in place, what people are already using, what skills they have, and also, of course, what are the objectives of the modeling. And again, this is a picture I like, you know, about engineering, you know, other engineers using models. So, what is a model? I mean, you know what it is, but what is my definition of a model? I mean, it's nothing really surprising, but it's an abstract and analyzable description of software artifacts, which are created for a purpose. And they are abstract because obviously details are omitted. It's a partial representation, and normally they should be much smaller and simpler than the artifact being modeled. Otherwise, it defeats the purpose. And it should be analyzable in the sense that it should lead to automate the task that you try to automate as an objective. I mean, you know, it should support automating some kind of expensive software engineering task. So, what are the objectives of that talk? I'm not going to give you a conference talk on a paper. I mean, I use that opportunity to try to reflect on several years of research in the area of model-based testing and verification. So I will go through a number of examples at various levels of details, because obviously, if I go through several examples, I'll have to stay at a certain level of abstraction. All those examples follow the research paradigm, you know, industry-driven research paradigm that I've described before, except perhaps the first example. All those examples have been conducted in collaboration with one industry partner in various application domains. And what I will do then, at the end of the talk, I will try to draw lessons learned regarding scalability and cost effectiveness, because this is what is in my title, after all. So I have to get back to it eventually. So all the there is a research pattern in all the examples I'm going to give. They kind of follow a common pattern. They all try to solve a verification testing problem by relying on a model, either of the system or the environment of the system under test. And they somehow rely on search to optimize some objective function. Whether it's to, find worst case scenarios with respect to some performance measure, or whether it's to reach a critical error state, but they try to optimize something. And they rely on search. And the search technology being used is complete or not, deterministic or partly random. But you will see that in most cases, for scalability reasons, and I'll get back to that at the end of the talk, we rely on meta-heuristics, and sometimes on constraint solvers, but we haven't never managed to actually scale up with that technology. And the idea is that you can only scale if you only search a small part of the search space in order to find what you're looking for. If you have to do a complete search, then most of the time, you cannot scale on real industrial problems. And what is the role of the model? The model here is not used as in model checking to prove a property or to symbolically execute a certain behavior. The model here is used as guidance to the search in order, for example, to find worst case, high risk scenarios in the space. So it's used for guidance. But I'll get back to that.
Do you mean nominal situations in terms of behavior?
For example, I'll show you an example of that. Let's say you're looking for scenarios that lead to deadline misses in real-time systems.
Yes.
Then you are looking for scenarios that are as close as possible to miss a deadline, or that actually miss a deadline in the space of possible inputs. I mean, as an example. But what worst case means is context dependent. Depends on what the objective of testing or verification is. But of course, the problem with those meta-heuristic search techniques here, and even with constraint solvers, because you can never search, you can never complete the search, usually within time constraints, is that it relies on heuristics. And what does that mean? That means to assess whether it's effective, you have to perform extensive empirical studies, because you have no way to analytically determine whether it's effective or not. So let me start with the first example. So this was one of the earliest work I've done, which matches that research pattern I've mentioned before. And actually, this is the only piece of work I will talk about which was not based on industrial collaboration, but that's the earliest one. So here, the point was to help with schedulability analysis. Well, not exactly, but with testing schedulability properties, but I'll get back to that. As you know, there is a very well-developed theory, mathematical theory of schedulability. So now, you can actually mathematically demonstrate under certain assumptions that a number of tasks are schedulable or not. But this makes a number of assumptions. For example, that all aperiodic tasks are ready to start at time 0 for that particular theory. Of course, execution times are estimates, and usually they are approximate. I mean, it's very hard to have precise estimates of worst-case execution times. Very difficult. So even though it's mathematically very well established, there is never a guarantee that you'll be schedulable, because it's always based on a number of estimates and assumptions. But in the context of testing, you are not only interested by knowing whether a set of tasks are schedulable or not. What do you want? You want to find worst-case scenarios that eventually you should execute in order to demonstrate schedulability. Why? Because, as I told you, even though that theory can tell you whether a set of tasks are schedulable or not, in the end you still need to test, because this is based on assumptions. so you have no choice. But the question is what to test. I mean, so it's not obvious. At a high level, the approach we took is that we had a model of the task architecture. That is, what are the tasks, their periods, their dependencies, what events trigger the execution of those tasks, And we used one meta-heuristic search technique, which is well known, genetic algorithm, and we adapted it to solving that problem in order to determine the timing at which events should be sent to the system in order to maximize the chances of missing a deadline or actually missing a deadline. So we search the space of all possible times for those triggering events in order to find the worst case scenarios with respect to deadline misses. Okay? And the goal was not to demonstrate, as I said, just that a set of tasks are schedulable or not. The goal was to find worst case scenarios so that we could eventually test them. I'm not going to go into those details because it's not very important. We modeled this using UML Mate, which is an extension for real-time system of UML. Because it's a standard, so why not? But you could model this in different ways. And the way it works, a little bit more in details, is that you have the model, which basically represents the task architecture. Sorry if I'm misusing the word architecture here, but you see what I mean. What tasks exist, how they are interdependent, their properties. You extract information you need for the genetic algorithm, estimated execution time, minimum interval time for aperiodic tasks. The genetic algorithm then searches the space, but it needs, each time it generates a solution, each time it generates a set of triggering times for events, it needs to estimate the fitness of the solution. Now, in our case, how bad it is in terms of deadline misses. And to do that, it needs to invoke a scheduler. A scheduler can be implemented in different ways. It can be implemented with a console solver, or it can be actually implemented in source code. Basically, the GA sends arrival and seeding times, or triggering times, and gets back start time and preemption times from the scheduler. And therefore, the GA knows exactly when tasks are running and can assess how bad the situation is. I assume here that you are familiar with things like genetic algorithms, how it works. Those randomized, guided search algorithms.
You're looking at probabilities here.
Yes. So I'm not explaining how this works, because I just assume that people have heard of that. So, of course, there are many issues here. I mean, it's not easy to use such techniques. You have to have a proper representation of your problems, chromosomes, in the terminology of genetic algorithms, and you have to have a proper fitness function. And that fitness function, to be effective, must be effective in guiding you through the input space. So you must have certain properties. So those techniques don't come for free. You have to think hard about how to use them in the context of your problem. I'm not trying to convey the idea that this is easy to use. I mean, it's not. I'll get back to that. So we need, I'm not going to talk about everything, I'm just going to talk about the objective function, the things that guide the search. That's all. So our objective function focuses on one target task at a time. We try to trigger a deadline miss for one target task at a time. So we have to run the search for each target task. We can start with the most critical ones. And what we want as properties, we want the objective function to be able to handle deadline misses, not get crazy values whenever you actually miss a deadline. We want to consider all task execution, not just the first execution of a task, all task execution during the testing period. And that is not just the first one or the worst case execution. And we want to make sure that when you have many good executions and one very bad one, the latter is not overshadowed by the others that you can, because one bad execution is enough to eventually miss a deadline. So for example, we devise a simple objective function which has those properties, where we look at the difference between the completion time and the deadline of each execution of each task, or the target task, sorry. t. And basically what we want here is that we want the search to minimize that value. And you see it's exponential, as you can tell here, which means that it's a way to make sure that the good executions do not overshadow the worst one. You see? So that's where it comes from. That's what we're going to try to minimize in the search. And we perform a case study based on a task architecture that was published by the ACI for hard real-time realistic avionics application. And it was, there were 8 high priority tasks that were deemed schedulable according to schedulability analysis. And when we actually used our technique, we found out that actually those set of schedulable tasks, 3 of them were missing deadlines. And you know, some of those tasks are computing the target of a missile of an aircraft. So you're not likely to reach the target if you miss a deadline. You know. And so we couldn't understand why, and we realized it's because the assumption of the theorem and the assumptions of the case study were not fully consistent. You know, like for example, whether avionic tasks are ready to execute right from time 0. Well, some were not. You know, it was startup period. You know, so it was a bit strange, but you know. Anyway, enough for that. We did some similar work on, by the way, deadlocks and data races. I mean, basically, we follow a similar approach for concurrency problems. But I'm not going to go into this. I have some references at the end of the talk. Okay. Another example, and this is actually an industrial project. So we were working with 2 industry partners, completely different in appearance at least. One was building bottle recycling machines, actually, you know, used in supermarkets. This is very common in Europe because, you know, labor is expensive, so just to be automated. And a completely different, you know, a completely different company developing marine seismic acquisition systems. But both were soft real-time systems with, you know, acceptable jitter in the order of a few milliseconds. So though they were quite different, they were similar that way. Another thing that made them similar is that, of course, to test those systems effectively, you need to simulate their environment. Because, you know, you can imagine that you're not going to test this by coming with bottles and feeding bottles to the machine. You know? It's not a very effective testing strategy, you know. So, you know, and something here actually, because it's very expensive to go out to sea with the large cables and the sensors. It's about $1 million a day. You know, so you don't test the system by going out of the boat and dragging the cables and the sensors. I mean, you don't do that. You know. So, you know, though they were quite different, they had similar problems, and so. Here, in that case, testing needed to be black box, because first the systems were complex, and the people doing the testing were an independent testing team. I mean, they were not involved in the development of the system, and they had no knowledge of the internal details of the implementation. Here, we're talking about system whose behavior is driven by the environment, obviously. I mean, those are just basically reactive systems that react to things that happen in the environment. The people doing the testing were software engineers, so as opposed to a project that we present later on in the automotive industry, those people, you know, were not using MATLAB or Simulink. I mean, they were software engineers. And here we see how sometimes the skills of the people performing the task can have an impact on the solution. You know. So what we needed to do, we needed somehow to have models of the environment, so not of the system, but of the environment. You know, all the hardware and the things that happen around the system, so that we could generate an environment simulator, test cases, and test oracles. And we didn't want to have several models, but to be the same model to do all this, because, you know, people cannot spend their time modeling. I mean, you know, It has to be cost effective. So the way we did it is that we basically, because in industry people like standards, we define a UML profile that is a lightweight extension of the UML to do that. And I'm not going to go into all the details, but one thing is that you have a kind of domain model first. So for example, for the bottle recycling machine, we had a domain model that basically told us all the things that the systems was interacting with. And for each of those concepts, we had a number of so-called non-deterministic attributes. And those are basically the variables that are determined by the environment. They are non-deterministic. They are determined by what happens in the environment. So for example, in the machine, you have a sorting arm. But that sorting arm can take a variable amount of time to move. And this is non-deterministic. It can take 280 milliseconds to 320 milliseconds. It's mechanical, it's not. So it's something that is part of the environment that is non-deterministic. Anything can happen in that range. And there are a number of other attributes that are non-deterministic. So the first thing you have to do is to model the elements in the environment and find what are the properties that are non-deterministic, things that can happen.
Is the model from the actual software, or is it just like
no.
higher level?
It's a model of the environment.
Yes.
It has nothing to do with what actual classes are implemented in the software. It may not even be object-oriented. No. So it's a form of domain model, but it's a domain model which is a bit special because we have additional information that are going to enable what we need to do. That is, simulate the environment and generate the test cases. Why? I'm going to explain that next. Well, sorry. I'm not good with animation. I went ahead of myself. This is,
But that you're showing the range there.
Yes, exactly. But of course it's not enough. For a component like sorter, you have a behavioral model, which is simply a state machine, but with additional features. So you have what you have normally in state machines, guard conditions, states, events, actions, but you will see that you have things like time transitions, with a keyword after, and you have the non-deterministic, for example, the non-deterministic attribute that was on the domain model. So we know that we take that transition anytime between 280 milliseconds and 220 milliseconds after we enter the state. And more importantly, another feature, and here, well, okay, too late. We have so-called error states. What are error states? They are critical states that you never want to reach, things that could turn out to be very expensive. Like the arm is moving to sort an item, and another item is coming. This is going to be trouble. You might actually, your machine might break down, and and you might have hundreds of machines in hundreds of supermarkets breaking down. So you never want to reach that. And what is going to be the goal of testing? The goal of testing is going to push the system using meta-heuristic search to push the system here. We do everything we can to bring the system here. Okay, and this is going to be the oracle, of course, the test oracle. So what we did, without getting too much detail, what is a test case? It's a simulation configuration that is all the non-deterministic variables. A test case is a set of values for all those variables. What it is. Okay? And in addition, some environment configuration. That is how many instances of each class in the domain model you have. But anyway, I won't talk about that. Generating test cases is basically setting non-deterministic attribute values. That's what it is. And the test oracle, as I said, is the error state. So we use search, as I told you, and I told you what the objective was already, is to bring the system into an error state, one of the critical error states. And of course, the space of the search is the space of all possible values for non-deterministic attributes. That's what the space of the search is. And we use different meta heuristics. Genetic algorithm is something simpler than genetic algorithms, but it doesn't matter. We define the fitness function, of course. And here I'm not going to go into details because this was very complicated. It was very complicated because in part of the OCL constraints. I'll just give you a vague idea of how we did it, but on the next slide. But this was a lot of work, which shows that those techniques don't come for free. And we performed that on industrial case study and some artificial examples because we wanted to create special situations that we did not encounter in our industrial case studies to see how our search would behave. But anyway, I'm not going to go into those details. So the fitness function, why was it complicated? For many reasons, but one reason was the guard conditions on the transitions. Basically, if you want to go close to an error state, you have to go through a certain path where there are, well, this is simple, but there are guard conditions, and you have to satisfy those guard conditions. And so, basically, the very basic strategy of the fitness function is first to have a component called the approach level. How close are you to the error state, the state machine? But it's not enough. If you have a guard condition, you have something called the branch distance, that is how close you are to satisfying the condition. And this is a mess. With a language like OCL, which is a high-level constraint language, it's a mess. Yeah. But it's so much of a mess that we wrote a paper for TSC. When you have something very complicated and very messy, you send it to TSC. So anyway, and time distance, because of course some of the transitions are time transitions. But I won't go into it. There are many more details than that. There's an entire paper just on that. So yeah. But anyway, so that was an example of an industry project. Second industry project, I might actually, what time is it? I might have to rush a bit actually. I think I'm going to skip that one. I'll skip that one. Anyway. Sorry. I've been too slow on the other ones. Yes. Okay. I'll get back to it if I turn out that I have time. So this is a project with Delphi, an American company in Luxembourg. Yes, there are American companies in Luxembourg. They develop powertrain systems, for injection, braking, cruise control. Yeah. So anyway, of course, what you have on modern cars, you have electrical control units that look like this, and the software that runs on electrical control units is getting more and more complicated for plenty of reasons. The software is more and more complex, and etc., and very critical in many cases, as you can imagine. So how do they test such software? There are 3 test phases performed by different people. One is called model in the loop testing, and here the environment is entirely simulated using MATLAB Simulink, because we are in an environment where the people are engineers, and it's a standard thing to do in the automotive industry. So you see, it's very different from the previous environment. Here we have control engineers and electrical engineers, and that's what they use. That's what they have learned at school, and that's MATLAB Simulink is their modeling methodology.
But their models are rigorously based on what actually happens in the industry. That is, the systems that they use in the industry.
Yes.
They try to make sure they match if the models match. Exactly.
Yes, but it's not always the case, though.
Yeah.
So here in model in the loop testing, the environment is modeled and simulated, and the software you are going to develop is also modeled, actually. So what you are testing is whether you correctly model with Simulink, the functionality you are eventually going to generate code for or write code for and deploy on the electrical control unit. Once you are sure this is correct, then you actually generate partly the code and manually write partly the code because the generation is not complete. And you do some more testing, software in the loop testing, and eventually you do hardware in the loop testing, which is the real thing with the real hardware, or a simulator that simulates physical signals, if it's not the real hardware. Of course, this is very expensive. The problem with hardware-in-the-loop testing is that you can only run a limited number of test cases. You can't run, you know. But on the other hand, with model-in-the-loop testing, you can run at night as many test cases as you have computing power. So the idea you're going to see, where I'm going to focus on model-in-the-loop testing. What we're going to do, we're going to use model-in-the-loop testing to try to identify worst-case scenarios again. And those worst-case scenarios are going to become the test cases we're going to test here. So we're going to use model-in-the-loop testing, not only to do model-in-the-loop testing, but to identify the test cases we need to run here that capture the highest level of risk, if you want. So, of course, like in many places, they have the typical problem. They do manual test case generation, it's expensive, blah blah blah. The functions captured in Simulink are complex. Eventually, all those have to be integrated at hardware-in-the-loop testing. What's interesting is that they had a lack of precise requirements, which I guess you can tell me when it's not surprising. But basically, when they run test cases, they just look at the result, and I will tell you what that means in a minute. And they say, yes, all right. But when you do testing, it's not enough. You need you need to define what all right means. Somehow. So we had to do that. I'll get back to that. So anyway. So we are going to focus on model-in-the-loop testing, and the ultimate goal of model-in-the-loop testing is to ensure that individual functions behave correctly and timely on any hardware configuration. So let's do that. So the thing is that in the software that runs on the control units, there isn't one type of function, one type of component. There are different types of functions that are very, very different, and in fact that require very different testing strategies. You have Simulink functions that do computations of various types, and Simulink functions that do controlling. And in the controlling category, you have, I'll use that slide for a change, you have state-based functions that are driven by state-based behavior, and you have functions that are continuous, that are called PID controllers or closed-loop controllers. And we decided to focus on this, at least in the results I will tell you in a minute, because nobody addresses that problem in software testing. In software testing, you always assume you can use computer science modeling to model what you're testing. But you can't use a state machine to model the behavior of this. It's continuous. This is actually characterized by differential equations. So we said, okay, we should try to find a way to automate the testing of this, because this is, interesting. Nobody has done that. And it's an example of a surprising problem that you never think about if you don't work with industry. I have many other stories, but I've never thought of that. But of course, they are very critical pieces of software. They control valves. They control devices that have an impact on the car. So typically, at the middle stage, you model your controller, you have a model of the plant, all this in Simulink, and basically you send comments to the plant model, or it's called a plant model, whatever you're controlling, and you compare the actual output with the desired value, and you provide that to the controller, who then decides what's going to be the next signal, the next comment. And that's why it's called a closed-loop controller. And so, as I told you, they didn't have any requirements. We just look at results and say, So ideally, over time, what you do is that you have the actual value, and you have the desired value, and you want to somehow reach the desired value. But of course, it's not enough to say, I want to reach the desired value. We found 3 properties that we call liveness, smoothness, and responsiveness that seem to capture what they were looking at when deciding whether a test case was successful or not. And it's probably better explained here. So you want to know that you will stabilize within the desired position within a certain time. Okay? So that's it. And then you want to make sure that you don't have Okay. That you somehow reach a certain level of precision also within a certain of time, and this is responsiveness for performance. Not just that you will eventually reach it, but that you will get close enough to it within a certain amount of time. And more importantly, you don't want to have big bumps like this. Why? Because it damages the hardware. So for that type of controllers, you don't want to have those big bumps, and we call that smoothness or safety, depending on who we talk to. So we use search again, always the same. I always follow the same pattern, okay, that I've told you at the beginning. Not that it was intentional, it's just that when I decided to prepare that talk and I went back to my research, I tried to identify what was common across all those projects. So it was a very useful talk for me to prepare, actually. It allowed me to reflect a little bit on what I've done in the last, 10 years, mostly the last 5 years, but a bit further as well. So here, what do? The input, the search space, I'm a bit jet lagged, so I'm not working very properly yet. The search space is basically the actual value, desired value, and configuration parameters. This is what the search space is for closed-loop controllers. So we search in that search space, and what we want is to break all those requirements. We have to find ways of destroying smoothness, liveness, and and we want to find the worst case scenarios with respect to any of those three requirements. And then we're going to take those and test them on hardware in the loop testing. That's the idea, So let me take first a simplified version of it, where we do not consider configuration parameters, just the actual value and the desired value, which or initial value and desired value. And so the way we did it, the first step, of course, I didn't tell you that, but we had to define fitness function for each requirement. As usual, when you do search, you need a fitness function that tells you how close you are from breaking the requirement. And for smoothness, this is, for example, the space of initial versus desired values, and the colors represent the fitness. And red is bad and good is good. Blue is good. Jet lag. Okay? And so first we did in 2 steps, and I explain why. It's a bit complicated. First, we did some kind of random walk or random search in the space, and we identified parts that seem to, be dangerous. Then we asked the domain experts, okay, which of those subregions should we explore? Because they are not all as important. Some subregions here almost never happen on a real car. Others are very frequent. Some are more dangerous than others for other reasons. For example, when you are here in that region, it's much more dangerous because that means if it's a valve, the initial valve is almost closed. And this is where you can damage your hardware. For example, if you are not smooth, in your control, if you have a big bump. So, at the first thing people say, oh, okay, among the red areas, I'd like you to focus on this because it's more dangerous, it has a higher probability of happening on a real car, etc. And then we used a meta-heuristic search to focus on those areas. Those, and we call that heat maps. We use heat maps to interact with the engineers because they like that representation. It was useful for them. And one thing we did also to make sure that our search was meaningful is that we compared our search, for example, this is one meta-heuristic search algorithm, with random. Because sometimes people use search and they don't compare to random, and then it works well because the problem is easy. So, so this happens often, And here, for example, for responsiveness is an example on one subregion of 50 runs, I believe. And here you can see very clearly that the search converges much faster with less variance than random, for example. So we have to do that type of analysis. So in conclusion, well, you know what we have done, but there were a few interesting things. First, among the regions that were dangerous, there were many different landscapes. You had landscapes that looked like this, with a clear gradient towards where you wanted to go, and you had landscapes that looked like this, a complete mess. And the problem is that the search algorithms that work well here do not work well here, and vice versa. Here you must have a search algorithm that is more explorative of the space, and here you must have a search algorithm that is more exploitative. So basically we are working on having an adaptive search that, depending on the landscape, goes one way or the other. And another problem is that we have is that here it's only initial and desired value. So you can show it graphically to the engineers. But what do you do when you have 50 configuration parameters? What do you show to the engineer? Or so we have to either formalize the heuristic they use, or I don't know, or use multidimensional visualization techniques. I'm not sure what to do with that. Anyway, new project here. Okay. It's again in the automotive industry. Can you see it? Oh, to hurry. As you know well, I'll go to the next one. The way those systems are built is that the car manufacturer develops its own software, its own components. And that software is proprietary. I mean, it's even secret. Okay? So they are not giving the source code to the suppliers, like Delphi. And they ask Delphi to develop other components, and they ask Delphi to integrate those other components with their components, their runables or executables. So there is, and we're talking about hundreds of runables to integrate. That's the scale. Okay? And it's going to get worse in the future. So what they do in the automotive industry is that there are so-called AutoSAR models. Those are basically standards that they have agreed upon in terms of what information to exchange about those executables, like their period, their interdependencies, because you cannot ask someone to integrate your software if you don't tell that person anything about your executables. So there is an agreement, and this is captured another form of an AutoSAR model, and that's what it is. And here is some of the information you have in an AutoSAR model. But that's and this is used to generate glue code that somehow puts together the runables of the car manufacturer and of the supplier, for example, Delphi. So let's skip that. So here what we want is that the way it works here, the way they deal with those runables, that is those concurrent tasks, they divide the time into so-called OS cycles, for example, 5 milliseconds, and basically they assign the runables to a cycle somewhere. So you can, of course, start all the runables at the beginning of the time period, but the problem with that is that it's a very imbalanced use of the CPU, and you may run out of CPU. I'll show you an example next. So basically the problem was to minimize the risk, and that's the title on the first slide, of CPU shortage. Because of course this can have consequences. This is real-time software. And if you do that, there are also other advantages. You can minimize the hardware cost. You don't need to. The maximum CPUs that can happen is, less. So you can minimize. You can put more. You can put more runables on the core. And since the cost is multiplied by the number of cores, it's a good idea. You can in the future add new functionalities, and of course you can reduce the possibility of overloading CPU in practice. So the way we do it here, again, is very special. It's not what you see in the research literature. You have those cycles of 5 milliseconds, and basically you need to distribute the runables. But it's not that simple. So by distributing the runables, the term that is used is offsets. You decide of offset values. That is, offset values are delays from time zero, where you start executing a runnable. And you need to do that in such a way that The runables respect their period. The runables respect the OS cycle, and they don't execute more than 5 milliseconds altogether within a cycle. And they satisfy their synchronization constraints, which have been provided by the AutoSAR model. And so, for example, this is an actual case for 430 runables. If you run all the runables, or you allow them to run from the beginning, this is the CPU usage over time. And here you go over the 5 milliseconds limit, that means you have a CPU shortage. And what we do is that we use search, of course, not surprising. And the search space is a set of possible values of offset values. Okay? And this is what we get. And here, of course, the scale is not the same. Here, the maximum is this. Here, this is the maximum. It's not the same. Okay? And I won't go into the details of what search algorithms we use and all that, because I want to have time to talk about something else. Anyway, we compared many search algorithms, both in terms of the maximum CPU usage observed and in the time to find the best CPU usage, or the max CPU usage, sorry. Because we need those algorithms to be efficient, not just to find the right solution. If tomorrow we deal with 5,000 runables, we have to be able to deal with it. So we have to converge fast towards the worst, or the best case scenarios, sorry. In that case, it's a best case scenario. So we compare with random, of course, as usual. We're going to go through that. So and here is basically the conclusion. And the problem we are solving here is going to get worse with time. Because in that industry, because software is getting more and more complex, the number of runables is going to increase. And because they have cost constraints, they are going to have to make use, to the best extent possible, of their hardware, and the number of cores they have. So that's why they ask us to work on this. It's not so much of a big problem now, but it's going to be a problem very soon. Anyway, so that's it.
Won't there also be more powerful cores and more?
It's expensive. On each core you have to have that hardware. So you can do that on the luxurious cores, but perhaps. So here I give you example of project. There are many other projects I could have used. Those are like the projects where I use model-driven engineering in the last 5 years with industry. Here are the companies. And you see there is a lot of testing here, but not only. Why? Because testing, after all, is still the verification technique that works best in practice. So that's, but some applications are more around safety certification. We had one very interesting project called automated configuration, a system where you have thousands of configuration variables on subsea systems to control the flow of gas and oil. What's interesting is that in many cases we use a profile of UML, not always. Here we have SysML, here we have Mate, here we have MATLAB Simulink, and here we don't know yet. It's a current project. I put it here because it's kind of interesting, but it's about verifying and testing legal requirements. That's a new project. And you see, in many cases, we have used meta-heuristics. Sometimes we have used constraint solvers, but we have found out, I didn't have the time to talk about that it doesn't scale very well. Sometimes the problem could not be re-expressed as a search problem or optimization problem. It had nothing to do with that. So we didn't use any of that. But still, very often you see meta-heuristic. It's pretty, So the conclusion with respect to modeling is that we were able, in all cases, to rely on standards. We didn't need to invent a new notation, a new language. But it was never UML only. UML by itself, plain UML is not enough. You need something that has more precise semantics and more specialized notation. You can't use just UML. And what it shows was driven by the information that was needed to guide the search optimization. What was the appropriate level of abstraction? It has to be, the models have to be of minimal size, just what you need for the task at hand, nothing more. Of course, the test verification objectives, the current modeling practices and skills, and whether they had to rely on some standards. And what we found is that in general, the modeling requirements were reasonable. There are nothing people got crazy about, actually. Sometimes they even liked the modeling sessions because it allowed them to learn about some part of the system they didn't know about. I mean, it was a very interesting learning experience for them. But anyway, about meta-heuristic search, this, of course, tended to be the most common technique we used for stochastic optimization, for optimization in general. Why? Because, in fact, the conclusion I come up with is that it's probably the most versatile and the easier to tailor to a new problem. It's much easier than coming up with a constraint model that fits that problem in the constraint solver, an efficient constraint model. But it's not easy, but it's more, somehow we were able to use it in some cases where we couldn't find an efficient constraint model in the constraint solver. It entails lower modeling requirements than, say, model checking, and I'll get back to that. The fact that we rely on search, that we only use the models to guide search, not the model to do symbolic execution or detailed static analysis or God knows what else. You know. Those techniques, they always give you an answer, no matter how much time you have. They always give you the best answer they can find, and without always exploring the same part of the space. You know. So that's practical. But of course, what people say that, well, but the problem with those heuristics is that it's not a proof. You have no certainty. But as I will tell you in a minute, you have no certainty no matter what, even if you use model checking. I'll get back to that, or whatever else. Because first, the models have to be fully correct to be able to prove anything. So, you know. But I'll get back to that. Oops. Oh, something has disappeared. Oh, what did I do with that slide? Oh, sorry. Missed a slide. Some slides that disappeared. It must be really jet lagged. Oh well. Okay, well, I'll just talk without the slides. I don't know what happened. Maybe that's the wrong version of the slides. Anyway, so and I'm going to conclude on this. What I ask myself is that, you know, because we try to think whether, on every project, we try to determine whether, should we try model checking? Should we try model checking? After all, it's a hot topic. Everybody talks about it in academia also. How come we never used it? You know, how come we never somehow found a way to use it? And the reason is that, first, even when you do model checking, there is no guarantee because the model is so complex. It's sometimes not simpler than the source code, that it can be as error-prone as the source code and who has tested the model. Okay? And because you want to do, for example, symbolic execution, your models need to be operational. They need to be very detailed. You know? When you bring models to guide search, they're not nearly as detailed. Not nearly the same level of detail and complexity. So you might say, okay, well, having that, you know, those very detailed operational models might be worth it if I get a guarantee. But you cannot get a guarantee because you don't know if the models are expensive. Correct, sorry. So then you find yourself in a situation, you say, okay, how am I going to justify to my collaborator I'm going to use model checking? I cannot tell him he's going to prove anything. You know, it's very complicated and expensive to model. You know, so how do I justify this? You know, and we were never able to justify it, never. So when I thought of that, prepared that presentation, I thought about it. I thought, well, you know, this is the reason why we never used it. You know, so here we do modeling, but it has nothing to do with the type of modeling you need to do model checking. Yeah. You have seen, for example, the models we used for modeling the environment and testing, you know, the recycling machine. You know, those models are not, you know, crazy. You know. I mean, of course, they are dedicated to our objective, but they are not crazy. Recently, for example, on one of those projects, for example, to give you an idea of the size. Here. That project is with a satellite company. Yeah. It's a current project I have. I could have used it as an example, but it's interesting as well. And here again, the problem is test automation. And we work on data acquisition systems that get data from satellites, identify transmission errors, and extract data from what the satellite sends. And here the complexity is not in the behavior. The complexity is in the structure and content of the input files and the mapping to the output files. That's where the complexity is in a data acquisition system. Very, very complex inputs with very complex mapping to log files and many output files. And so that's what we modeled. We modeled the structure and content of the files. We use a UML. We use UML in that case, or UML profile. And we modeled the mapping. And that's what we used to automate testing. And for the system we used, we had, 68 classes and 52 constraints for the whole system. Yeah. I mean, of course, there are other elements as well, just to give you an idea. I mean, yeah. Nobody among our partners complained that this was too complex, too big, or, Obviously, it's much smaller than a system model, a real system model. Yeah. So, anyways, this was another example. So, I guess I'm done, and I'm almost on time. Thank you.
We got time for questions.
How did you use subject matter experts in all of this? That their knowledge is inherent in your meta-heuristic approach. To one extent or another.
Yes, the question is, how do we work with experts, and how do we make use of expert knowledge? Yeah. I'm just repeating for everybody. Of course, you have seen that we work very closely with our partners. Yeah. I mean, they are, we even write papers with them. I mean, some of the names here are names of our partners. So we of course rely on their domain knowledge. I mean, for example, for the closed-loop controllers, the requirements came from them. We formalize them, but we try to make sure they were correctly formalized. But so we work very, very closely with them. I mean, we of course we have to some extent to get acquainted with the domain. But we're never going to substitute ourselves to the experts, obviously.
Do they learn, if you find a structure that can be imposed on their discipline, on their knowledge that helps them, do they learn from that? Have you ever been?
Yes, we actually spend time giving tutorials, mentoring them. Super. We share our time between research and knowledge transfer in both directions.
Yeah.
So we try to learn from them, to understand what's going on, and then we try to teach them something as well, so that they get something out of the collaboration as well. So that's what we do. We always end up, whatever modeling methodology we use, for example, we always end up teaching in a tutorial. We have to. We have no choice. We have to tell them how to model, otherwise. And this, they don't have to know. It's internal in the tool. They don't need to know how search works. It doesn't matter to them. But the modeling, they need to know. They need to know how to do it. Yeah.
It seems inherent in all model-based testing that there are problems that are particularly well-suited to modeling, and thus such approaches, maybe model checking, or I'm wondering, like all of these systems here, there's some kind of definition of what it means to fail. So you either get into that error state, or your arm swings too far and you end up damaging, or these things bang together.
Yes.
Too much CPU usage. Do you find in practice that you run into some of these like non-testable type things where you don't have an oracle, you don't know what the correct thing is? Do you spend a lot of time trying to figure out the difference between what problems you can solve and what problems you can't?
First, what I want to say is that I listed the projects I've run that use models, but there are projects I've run that don't use models. They are not listed here, that's all. So I'm not saying that I had to use models on every project, or I could use models on every project. But I could use models on the vast majority of projects, though. Okay? And there is an example like this recently. I go and talk to Goodyear. They have a center in Luxembourg as well. And they build simulators. What is an oracle for a simulator? So here you think of metamorphic testing, perhaps. It's just an example. So yes, of course, that happens. Sometimes models, that type of models at least, they just don't apply. You can't use that to automate testing.
But you're saying that often you could find a model that.
Yeah, often yes, often. Yes, at least on the projects I've run over the last 15 years. There was another example. I worked with Siemens, and they were developing segmentation algorithms, to identify tumors and 3D images and all that. And I thought, I was naive, I thought that segmentation algorithms were exact science. It was a mathematical model. In fact, it's a big cooking recipe. They keep changing all the time. And what their problem was, and I couldn't use model-based testing for that, what their problem was, it was that, so they would keep changing the segmentation algorithm because they would find an image where it doesn't work well, so they would tweak it. Yeah. And then, they had a big benchmark of images, and you know what they had to do to verify because there was no oracle, what they had to do to verify the new segmentation algorithm, they had to pay a medical expert to go through the segmentations, correct, not correct, correct, not correct. Of course, very expensive. Sure. So we use machine learning to learn how the expert decided that the segmentation was correct. But there was no modeling. There was no modeling that way, involved. We had to define distance function between segmentations, and then use machine learning to learn how the expert decided that an image was medically correct. Of course, it's never fully correct, but it's close enough so that you can make a good diagnostic, or not. That's what we learned. And then they could use that, after that, to automate the verification of the segmentation algorithms. But here, no modeling involved, no modeling of that kind at all. What can you model? There is no universal solution to test automation.
It's also appropriate to gauge the gauge, that is the expert that did all this stuff.
Yes.
Need to verify that he's in line with the vast majority of practitioners.
Also, yes. So, but here today I decided to talk about model-based testing and verification, so that's why. Yes.
I don't know quite how to formulate it, but
you're trying to be polite?
No. They know I'm not, so that's easy. I'm trying to figure out so it's kind of a two-part question. What have you learned about the modeling languages that are available, and what do you have to say about them? And the counterpart to that is sort of, how difficult is it to model? I don't know quite how to ask that question, but it's sort of, there's a lot of smarts that went into that.
Okay, so in terms of modeling languages, you know that people in academia criticize a lot UML. It's vague, there are no semantics, blah, 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 blah. And here is a 20 pages paper with detailed semantics based on some mathematical model, and now we have solved the problem. So by first, I never had a problem with semantics. Because you know how you capture semantics in practice? As an engineer, you don't use denotational semantics, or you don't use a mathematical model, because the model is so complex that it might actually be wrong, the semantics. So the way you define semantics in practice for a given problem, you describe a modeling methodology. What to model, at what level of detail, when, for what, with examples. That's how in practice you define semantics. And if you do that, it works. It's fine. Again, the models don't have to be perfect. No? The models don't have to be fully correct, as opposed to model checking. Models here are used for automation. They are not used for proof. So sometimes you have a failure because you have a mistake in the model. And as long as it doesn't happen too often, it's fine. But you have heard that academics criticize a lot. And in fact, there are variation points in UML, but it's intentional. It's supposed to cater for all needs and everybody. So of course you cannot define precisely all the semantics. It's not possible. So that's why you have the word profile here often. That's why. But that means that we have a modeling methodology and we specialize a bit the notation to capture all the characteristics we need to capture. Yeah, that's why we do that word often. It's an extensible language. And what was the other one? How hard it is to model. Modeling is something you need to learn. Yes, like programming, like it's a skill. So yes, it doesn't come for free. That's why we give tutorials. Now, not everybody is capable of modeling. Not everybody is capable of abstraction. But the people who do the modeling here, you don't just pick a random developer. it's like an architect with blueprints. I mean, it's not anybody on the construction site who's going to draw the blueprints. You know, and that's why you train. You have graduate students, and you know, so it's a skill. But from my experience, of course, I have met people who had limitations sometimes. But you know, we tend, you know, when you work with engineers, I mean, with people with a certain degree of education. I've never noticed that it was beyond their capability. Yeah. But of course, if you pick the guy who just went to, we did a 2-year degree at the university college to learn Java, I mean, you know, it's a bit difficult. You know. You have to be capable of a little bit of abstraction. You know. But engineers, for example, what's great when you work with people in the satellite industry or automotive industry, they're all engineers. And those guys have no problem with abstraction. I mean, it's like, you know, it's like they can do it, you know, hands in their pockets. You know, it's those guys are easy. When you work with banks, it's not more.
How do you spell abstract?
It's not the same thing, you know.
Fair enough.
Anyway.
Any final questions?
Very good.
Lionel, thank you very, very, very much.
Yeah.
Thank you.